Okay, I'm Scott, and I'm going to talk to you today about the engineering that goes into the instrument, the SUDA instrument, that's going to Jupiter's moon Europa on the Europa Clipper mission. I'm also going to talk to you a little, well actually quite a bit about the science. Sasha Kemp, who's the PI, is in the back, and he presented in this same forum a couple of years ago and talked a lot about the science, of Cassini and the CDA instrument, and how that tied into Europa. Understanding the engineering of the instrument isn't as cool unless you know about the science. So I'm going to touch on the science. If you want to ask questions, go ahead. If you stump me, Sasha can help me. But I'll give you a nice overview of science and the Europa mission as a whole. Okay, so this is from 2001 Space Odyssey, which I believe 50 years ago yesterday premiered. So anyway, I thought I'd put that in there. Okay, habitable worlds in our solar system. We know about one of these. Actually, I think I have to click over here. Earth, okay. Enceladus. So this has been studied by the Cassini mission, and we understand that there is an ocean underneath the ice shell of Enceladus, and the Cassini spacecraft has flown through the plumes in the southern pole of Enceladus and sampled and measured the composition of those plume particles. And so we understand Enceladus, although there's still quite a bit to learn, but lots been done. Europa is the other one that we know has water, or pretty darn sure it has water. Moon of Jupiter, and that's where the Europa Clipper mission is going to go. So just a real brief history of Europa exploration. Discovered in 1610 by Galileo, along with the other Galilean moons. This image is not from Galileo, but this might. Oops, let me go back here. So his telescope probably did not look this good, but that's about give you an idea of what it might have looked like. Fast forward quite a ways to the 1960s. I'm sure there was a lot done in between, but ground-based observations determined that Europa's surface was mostly water ice. Okay, Pioneer 10 flew by Jupiter, took the first close-up image of Europa. 1979, Voyager 1 and 2 flew by Jupiter, took better images, discovered some interesting things. There weren't large impact craters, and there was some darker bands and darker coloration on the surface. So then Galileo. We learned a lot about Europa. The surface is geologically young. We know this because there aren't many craters. The moon should be as old as the other bodies in the solar system, and so it should, if it was a static surface, it would look like our moon, just completely covered with craters. It's not. There's evidence of cryovolcanism and plate tectonics, and so the surface is water. It's clear from topology on the surface that water's leaking up, creating deposits. There's evidence of tectonics, plate tectonics, movement, upwelling, all sorts of interesting features. Galileo additionally had a magnetometer on board, and through magnetometer measurements, it's pretty conclusive that there is a salty ocean, and so the induced magnetic field from that salty ocean was picked up by the magnetometer, and so underneath that ice shell, somewhere between tens and 100 kilometers thick, is a salty ocean. Okay, so what might make Europa habitable? It's got water. Okay. Chemistry. And so the ocean is likely in contact with a rocky mantle, and so that's interesting from a chemistry point of view. And energy. So the water is still liquid, and so there's likely an energy source in the core. So tidal heating is the cause of that. And so all these ingredients potentially lead to habitability. Okay. Okay, here's a more complex chart that I borrowed from Bob Papalardo, he is the program scientist or the project scientist for Europa. And this is working from the bottom up here. You can see there's a rocky mantle, there's hydrothermal, and there's activity down here, different, so methane, iron, different things. There's some convection and circulation of the ocean, likely. So some of this is speculative, but it's what could be happening. Cracks and fracture networks, potentially plumes erupting from the surface. And then at the surface, Europa, and I'll talk about this later, is in a harsh radiation environment. So radiolysis of different molecules is going to happen at the surface. And so there's all sorts of interesting things happening at Europa that could make for interesting chemistry and potentially a place that could be habitable. Okay, people have likely heard about plume detections on Europa. This is still open to debate, but in 2012, there were some Hubble observations that detected a water signature near the south pole of Europa. There was a subsequent observation that they didn't see them, and I think there's been observations since then where they saw them again. Ben Southworth, who is in Sasha and Mihai's group, has modeled what these potential plumes might look like. This is a simulation. What's interesting about this is that the Europa mission plans to fly by as low as 25 kilometers. So if plumes are present and we can time it right, we might be able to fly right through one. If you got questions, feel free to interrupt me. Okay, so Europa's interesting. And so NASA, ESA have been looking at various mission concepts for Europa for at least 20 years, including orbiters, landers, joint NASA and ESA missions. But now things are moving forward. And so Clipper is moving forward. It's in development. It's funded in NASA's budget. JUICE is in development by ESA. This is the Juicy Icy Moons Explorer, which in the current plan is to do some Europa science. Its primary target is Ganymede. And then the Europa lander. This is under study right now. It's a couple of years behind Clipper, but this is also funded by NASA. Okay, so the Europa Clipper mission, just a brief overview. It's a NASA flagship mission. Its objective is to investigate the habitability of Europa and to do full reconnaissance and completely characterize the moon. It goes into a Jupiter orbit. So NASA studied orbiters. The radiation environment is quite harsh. So technically, an orbiter is very difficult. So solve this problem by going into a Jupiter orbit and flying by the moon very closely and into what, well, let me just talk about this for a minute. So this is this kind of spirograph looking thing is a buildup of 45 orbits around Jupiter, 45 flybys around Europa, more orbits. Some of them are used just for gravity assist maneuvers. But the center dot here is Jupiter. The next circle is the orbit of Io, which is the innermost moon. The next orbit is Europa. And so these larger ellipses are the spacecraft orbit. And so it's in a 4-to-1 resonant orbit. So Europa has 4 orbits for every orbit of the spacecraft. And it's timed such that at the perijove, or near the perijove, it flies by Europa. And so that means that it only spends a relatively small amount of time in the harsh radiation environment, which is caused by Io. There's 9 instruments on the mission, plus potentially gravity science, so that would be a 10th. We're all working towards a launch date in mid-22, and currently the mission's in phase B. And so this scheme here of just flying by Europa and not orbiting Europa still accomplishes near global coverage of the moon. So all the imagers, we almost get full latitudinal and longitudinal coverage of the moon. So the hard part are the leading and trailing hemispheres, but certainly the anti-Jovian and sub-Jovian sides are covered very well. Okay, so getting there. 2 ways. with several different launch vehicle options. So the baseline plan is to fly on a direct trajectory with the Space Launch System. And so this is the launch vehicle that's in development at NASA right now. And we would launch on a SLS Block 1B, it's called, and potentially a Block 1. And the way this works is we launch from Earth, go into a transfer orbit, and then it takes about 2.5 years of interplanetary cruise, and then we do a JOI, which is a Jupiter orbit insertion. And then the orbit is very big at that point. We have to pump down the orbit, make it smaller, get into that 4-to-1 resonant orbit, and then science starts. So that's the pump down period. So that's about 2.5, 2.7 years to get to Jupiter. Okay, the other option is to use a Delta IV Heavy or perhaps a Falcon Heavy. And these vehicles don't have as much capability, and so it takes a lot longer to get there. We need energy, so we need to do an interplanetary cruise. And this cruise, this type of trajectory, is called an eVega, which is an Earth, Venus, Earth gravity assist. And so get some energy from some heavy planets, and then do the outer interplanetary cruise to get out there. And this takes 7.5 years. And so the instruments, the spacecraft, everything is being designed right now for both of these. And so we want to be compatible, we want to be flexible. It helps us stay on schedule and make sure that our schedule works with launch vehicle schedules. Okay, so this is the Europa Clipper spacecraft. Let's start over here. Here's the launch configuration, folded up solar arrays. So it's a solar powered spacecraft. This is different than Cassini, which was nuclear powered. It's different than Voyager. Juno is solar powered, so it's sort of paving the way for Europa Clipper to do that. It has some pluses and some minuses from an engineering point of view, but certainly it makes for, you need a very big array. There's an instrument deck, a nadir deck that points, so the spacecraft, when it flies by, it does a pitch over maneuver, and so the spacecraft design is simplified by the spacecraft making a maneuver every time, so we don't need a gimbaled platform. One of these instruments is gimbaled, so it can do cross-track imaging. There's other instruments up here, so here's where SUDA is located. There's a neutral gas mass spectrometer right here. Big high gain antenna. There's a magnetometer boom with magnetometers on it, and one item here I'll get to in a bit is there's an ice penetrating radar, which works on 2 different frequencies, so it has 2 different sets of antennas. So it's got VHF and HF antennas that are attached to the solar array. Okay, so 25 meters of solar array is pretty big. So it's about a basketball court, just a little shy of a basketball court, just for scale. All right, let me talk about the payload a little bit. So ICE is the Europa imaging system, and it's really 2 instruments. It's a wide field camera and a narrow field camera, and the narrow field camera is on a gimbal. PIMS. This is a Faraday cup plasma instrument, and so this instrument is used to actually make corrections to magnetometer measurements. So there is a very dense plasma around Europa, and so that induces a big magnetic field. You have to measure the plasma, understand that, so you can subtract it out of the measurements from the magnetometer. So the magnetometer is trying to get at the subsurface ocean. All right, MISE. This is a mapping infrared spectrometer, and so it's doing surface composition measurements, so remote sensing, looking at it's a pretty high resolution infrared instrument that's trying to measure the composition of the surface. So here's a magnetometer called IceMag, and it's several magnetometers. It's got I believe 2 vector helium magnetometers and 2 fluxgate magnetometers, all on this boom. Europa UVS is this is a UV spectrograph instrument. It's it's looking at the exosphere. It's going to look at plumes, and so it looks at the change in the spectra of stars as they move through the limb of Europa, and absorption bands. So mass specs. This is a neutral gas mass spectrometer. So this is also from Southwest Research. So this is doing similar science. This is complementary science to SUDA. It's looking at gases that are in the atmosphere and the exosphere around Europa, whereas we're looking at particles. Okay, eThemis. This is a thermal imager that's going to look at the temperature of the surface and look for thermal anomalies, which might mean activity on the surface. Reason, that's the ice penetrating radar. And so this radar is going to look, it's going to sound down into the ice, and it's looking for pockets of water. It wants to, depending on how thick the ice crust is, it could potentially find the bottom of the ice crust and where the ocean is. And finally,
how deep can that go, do you know?
That's a good question. I believe it can go something like 20 kilometers, and so if the ice crust is 100, I don't think it's going to get to the bottom. And then SUDA. It's a surface dust analyzer from CU and LASP. Okay, I'm going to change gears now, and I'm going to talk a little bit about making compositional measurements, dust measurements from orbit, and try to explain to you how SUDA makes its measurements. Borrowed some content from Sasha here, which I think should be helpful. So there's really 3 ingredients for making this work. So one, you need ejecta clouds. And so ejecta clouds, so we need dust around these bodies. And it just so happens that these airless bodies do have dust around them. I'll talk about that in a minute. If we fly through that dust, and that with a spacecraft, we can sample it. And so when that dust hits the back of the instrument, we can actually measure the composition of that dust. Okay, and then we can actually determine, we can make a velocity measurement of the dust as it enters the instrument. And we can backtrack the trajectory of that particle back to the surface. And so we know about where that particle came from. This is a mass spectrum. These are mass lines, and so these represent the elemental and molecular composition of the particle. And we can say, with some sort of with some error bars, we can say where it came from on the surface. So this is ground truth. And so this other instrument, the IR instrument, it's making measurements as well. It's making higher resolution measurements, but we can tell that instrument, this is exactly what is at this place on the surface. And so they can use that to reference their data set. Okay, so let's talk about these 3 ingredients. So the ejecta clouds. So in the Galileo mission, these were observed. There was a dust instrument on Galileo, and so all the Galilean satellites are wrapped in dust exospheres. Okay, and the density of these dust exospheres fits a model, a physical model. It works. Things generally correlate. So these are all. There was, I believe, 12 Europa flybys on Ganymede, or on Galileo, and so we know pretty well what we're going to see in terms of dust density when we get to Europa. Okay, so they're there. How much material? So these micrometeoroids come in. So blue line here is a micrometeoroid. So the entire solar system is populated by micrometeoroids. They're flying around. They're moving in ranges of 10 to 40 kilometers per second, maybe faster if they're in a retrograde orbit. And these things are impacting the Earth, they're impacting the Moon, they're impacting all these bodies at Jupiter. Okay, so these tiny micrometeoroids hit, they make a little crater. They blow out ejecta. It turns out that what they liberate from the surface when they hit is something like 4,000 times the mass of the particle as it hits, because they're moving so fast. Okay, so this is always just continually generating new particles that are being ejected. Most of these particles don't make escape velocity. They're gravity bound to Europa, so they follow ballistic trajectories, and they're just there for the taking. So some SUDA flies through at a, the spacecraft flies through, and SUDA is there at 25-kilometer altitude. We expect to see something like 40 of these particles per second at the closest approach. Okay, so composition. This was demonstrated on the Cassini CDA instrument, and so this is the CDA instrument. It just recently was, along with the rest of Cassini, landed on Saturn, and so Cassini flew through these plumes on from Enceladus. So this is the south pole of Enceladus. This is a backlit image that shows this plume activity. So this instrument flew through, sampled the composition of these ice particles. So the plume physics is fairly well understood. Where the particles come from, whether they come from water that freezes as it's ejected from the plume, and so it is the content of the ocean. And so this is flight data from Cassini. It's a bunch of spectra added together, and then this spectrum was taken and compared to lab data. And so this is a laser experiment where the composition of water was modified in an iterative fashion until two spectra were created that matched. And so this allows, from ground experiment, to determine what the ocean of Enceladus, what the composition was, and what the pH was. So pH is about 9, the salinity 1%. And so this is something that can also be applied to Europa. Okay, now ejected backtracking. Okay, so same thing. Little meteorite hits the surface. Okay. All right, let's get it. So the green. So a little vector math here. The green arrow is the velocity of the satellite flying by. This is the spacecraft flying by Europa. This meteorite hits, it ejects a particle, VE, and then the difference between these two vectors is the impact velocity. So we measure that impact velocity as the particle passes through the front of the instrument. And so we know what it is, and because we understand classical mechanics, we can track that particle back to the surface.
Question?
Yep.
Are they analyzing all of these ejecta individually, or is it doing it in mass?
It's individual. So every one of these, so every particle that hits is an event for us. And so we capture that event and we send the data to the ground. And so we're not, unlike the neutral gas mass spectrometer where it's continually, it has an integration time where it's letting gas into the instrument over a period of time to get a better signal to noise ratio. We take spectra on a particle by particle basis. Now we may do some ground processing of the data to do some adding of particles that are similar, co-adding. But the instrument is really an event-based instrument.
Does it do that immediately?
It does it immediately.
Particle is just...
Every particle is captured immediately, and it's a bit of a trick from an engineering point of view because the particles are coming pretty fast, and every event actually is a decent-sized chunk of data, and we have to move that data around pretty fast inside of the instrument. And so, in a rad-hard design, fast electronics are tough. Yep.
How do you do the chemical analysis on those particles?
Oh, I'll get to that. I'm gonna try to explain it.
Okay.
All right. All right. So this is a sample of an actual flight data from the Cassini CDA instrument of its velocity sensor. So the blue line represents the path of a particle entering an instrument. These particles are charged. So as soon as they leave the surface of the moon, they're being hit by UV photons. So they're photo emitting, and so they charge up. They go into they interact with the plasma. So they're like little Langmuir probes. So they have charge. They enter the instrument. We can measure that image charge as it passes by a grid. And so this is that measurement shown. And so this is Cassini actually makes a multi-dimensional vector measurement of velocity, but this is what that signal looks like. Okay, so putting that all together from a compositional mapping point of view. So here's some simulations of what might happen on the surface of Europa. So a couple interesting features, the Theramacula and the Thrace macula. So these are these dark splotches here, which are potentially geologically young features that might be interesting for us to fly over. And right now, the design of the mission has us flying directly over these features. So the white lines here represent ground tracks for the spacecraft, and so we fly over. And so this is a simulation. So every one of these little dots here is a particle in the simulation. All right, the red dots are particles that come from Thera and Thrace, and the yellow dots come from outside. So particle type A, particle type B. All right, so we measure something inside of the instrument. We measure the velocity. What's the probability that it came from that location on the surface? And so with reasonable probability, we can as a let me see, the resolution gets smaller with decreasing probability, but we can track them back to the surface and say, well, look, these red particles did come. We know that came from Thera, and so that's a very useful technique, powerful technique. All right. Okay. Now a little more engineering. So, instrument overview. So what is this instrument? It's a time-of-flight impact ionization mass spectrometer. Okay, and I will attempt to explain that. And it's split into two pieces. We have a sensor head. This is a thing that's out on the side of the spacecraft. This is basically it's empty. It's full of electric fields and grids, and in the back of this is a target. But this is where the dust enters. This is where we're actually making measurements. We have a remote electronics box which lives inside of the vault, which is protecting those sensitive electronics from radiation. And so out of that instrument comes these time-of-flight mass spectra. All right, so SUDA's purpose, it measures the composition of particles ejected from the surface of Europa, and it connects those particles to their origin on the surface, and that's what we're after here. Okay, few more details, just kind of engineering graphics here for fun. Just walk you through this. So the front of the instrument, we're contamination sensitive. We have a door on the front of the instrument, and so we close that door for a lot of the ground testing to protect the instrument. We leave it closed during launch. We leave it closed during an interplanetary cruise. If we have to fly by Venus, for example, we want to protect the inside of this instrument from things that may come off the spacecraft. So the spacecraft has materials that are going to off-gas, and so we worry about those products entering our instrument. We're trying to measure part per million sensitivity inside of particles, and so we really worry about contaminants landing on the back of our target. So we have this cover that protects us. We open that cover once we get far enough away from Earth, and once the spacecraft is deemed sufficiently clean. There's a velocity sensor first, and this also includes some entrance grids that I'll talk about here in a bit that helps protect the instrument from the radiation environment. Here's the charge-sensitive amplifier that I talked about that makes that charge measurement on particles as they enter the instrument. And then this is electrostatic optics. This is where we focus our focus ions. There's a target in the back of the instrument. Of course, we need some structure to mount it to the spacecraft. And then key ingredient here is the ion detector, which actually does the detects and makes the time of flight measurements. So inside of the vault is the remote electronics. It's got 3 electronic cards about this big. Inside of it, we have a processor board, which does all the digital work, as well as analog to digital conversion. We have got a low voltage power supply and a high voltage power supply. Okay, there's a lot going on here. So how does SUDA work? All right. So particles enter the instrument, they pass through a series of grids, and they impact our target. Some of them aren't going to hit the target, some of them are going to impact the grids on the way through. That's okay. All right, so the velocity measurement, we've got 2 T1 here. When this particle passes the velocity grid, that's T1. When it hits the target, that's T2. We understand that distance very well. And so T1 minus T2, all right. And then we know the time, so we know the time it takes, and we know the distance. We can calculate the velocity in this direction. Okay. We've got rejection grids. I'll talk about those more in a minute. And then we have this ion optics. Okay, and this is for focusing ions. So when this hits, and I'll talk a little bit more about this, what happens when a particle hits the target here. But ions are, we generate ions, we accelerate those ions, and then we focus them back to the detector. Yep.
You know it's the same particle at T2 that it was at T1?
That's a good question, because that event happens so much faster. So that T1 to T2 time is very short compared to how frequently particles come into the instrument. And so there's very little chance that we'll get overlap. We could see overlap, and it's something that we potentially have to tease out on the ground to make sure that we either don't have overlapping spectra or overlapping data from the velocity measurement. So we have high voltages all over this instrument, which we use for our electrostatic optics, for rejecting plasma out of the instrument. And there are some electronics that live out in the sensor head, and these are some of the most challenging pieces. These are really sensitive analog electronics that are out in a very harsh radiation environment. And so we spend a lot of time and effort qualifying and testing these parts. We're doing radiation testing on them, and to make sure that they're going to work in this environment. Okay, so let's talk about what it means to be a time-of-flight impact mass spectrometer. All right, so when a dust particle hits a target, okay, that's a very energetic event. Okay, so we're talking about something that's moving faster than 1 kilometer per second. The difference in velocity between the Europa Clipper spacecraft and Europa when it flies by is about 4.5 kilometers per second, and so which is kind of a sweet spot for us from a science point of view. And so this dust particle hits, and that breaks this particle up into constituents. It's energetic enough that it actually forms a little puff of plasma, so it's kicking electrons out of the outer shells of molecules and elements that make up this dust particle. Okay, and so that's so we get this little puff of plasma. Okay, so what do we do with that? All right, so there's the target. We apply a voltage to this target. In this case, it's at 2,500 volts. And then we put a grid in front of that target that's at ground. Okay? Then a particle comes in, it hits, we get an impact plasma. And so this impact plasma has negative charges in it. It's got anions, cations, electrons. Okay? So in this case, the negatively charged ions and the electrons are going to get pulled right back to the target. But the positive ions are going to get repelled. They're going to get pushed away. They're going to get accelerated towards that ground potential. Okay? And they're going to get accelerated, and as soon as they go from 2,500 volts to 0 volts, they have an energy of 2.5 kilovolts. Okay? So here's one particle. This is a lightweight particle, positively charged. It's got 2,500 EV, and then, you know, if you've taken a high school physics course, you know that kinetic energy is 1/2 mv squared. Okay? So it has to have this energy, because this was the potential when it was accelerated, and it was accelerated to ground. Okay? Now here's a heavy particle. It also has 2,500 electron volts, but its mass is different. Okay? So the lightweight one flies faster, and the heavy one flies slower. Okay? So the flight time of each of these particles depends on the square root of the mass. And then there's a special parameter called the stretch parameter, which is a function of the instrument geometry and the voltages. And so we can achieve a finite mass resolution that's only really driven by the characteristics of this plasma that happens when it hits. And so if this plasma is very cold, then we get very narrow mass lines. And so we can distinguish two neighboring mass lines very, very well. Okay, so that's just sort of a generic example. SUDA expands upon this. We have a reflectron design, which improves the mass resolution. And just let me show you how that works. Dust particle, impact plasma. Okay, in this case, our detector is back here towards the target. And so we accelerate these ions out here. Then we have another electric field. another field which actually turns those ions and focuses them back to the detector.
What's the target made out of?
Good question. It's coated in iridium, and it's made of titanium. And we chose well, iridium is the key, and iridium is very inert, super hard, and it has a really high melting temperature. And so this is all great for this kind of science because it means that when this dust particle, let's say we had something soft back here like aluminum, what we would see in our spectrum is stuff from the particle as well as aluminum, or any of the impurities that are in aluminum, or if it's aluminum alloy, the minor constituents in that alloy. So we put as pure as we can get. It's, I think, 4/9 pure iridium, and we put it on titanium. So iridium is, from a cost point of view, it's about like gold per ounce, and we have spent a lot of time and effort trying to figure out how to do this, and we've recently been successful. And so we've actually made the target we're making is about it's 235 millimeters, so it's about 10 inches in diameter, and additionally it's got a mirror finish, so it's a 5 nanometer RMS finish. It's beautiful, and we've taken this to the lab. The beauty of iridium is it hits, and all you see, unless you get really fast dust, is basically the particle itself. And if we see iridium, we know it probably didn't come from the icy surface of Europa. So, okay. So in fast ions, they fly a little further into that turning field, but it's the same principle. It's a longer distance, longer flight time, and so we get a better mass resolution. Okay. So what do you get after that? So we have this detector. I could spend probably a whole hour on the detector, so the detector is sensitive to electrons. It's sensitive to ions and protons, and then so when one hits the front of the detector, it generates electrons, and then we cascade those electrons. So we actually multiply those electrons down a series of diodes inside of this detector, and then we read out an anode at the bottom of the detector, and that gives us a little signal, and we digitize that signal, and what we get is something that looks like this. And this is actually lab data from the prototype that we built, and this is a spectrum from an iron particle that we shot in our dust accelerator over here across the creek, and so this is an iron line. These are isotopes of iron. There's some sodium and calcium, so these alkali metals are really easy to ionize, and they're likely it's contamination inside. The dust isn't perfectly clean, the stuff we're shooting at it. So this is what we get. Okay, this is, if you can't read this is time on the x-axis here, and this is just amplitude. Okay, so this is not from our instrument, but this is a lab experiment. This is a smoking gun spectrum. This is something that Sasha's dreaming of, this spectrum. He wants to see this when he gets to Europa. This is really interesting. So all the green stuff you see here, these are all amino acids. Okay, the red stuff over here, these are fatty acids, and this is really interesting in that the even ones are higher peaks than the odd ones. This is an indicator of potential biological activity. And so if you see something like this in data from Europa, people are going to get pretty excited.
How high in AMU does your detector go?
So we measure up to 500. Our science really, we don't see much above 200, but we designed the instrument to measure out to 500.
Did you use an off-the-shelf dynode and the detector in there?
It's custom, it's in-house development.
Oh, is it really? Okay.
Yep. Yeah, and it's been fun.
How did you determine what size particle would be hitting your detector? Like, how do you know it's not going to be too big? Or?
Oh, so good question. So, so that Galileo. So several slides ago, I showed you, that sort of number density plot as a function of altitude from Galileo. That instrument was also measuring the size of particles, and so we understand the size distribution. And so it's real. So there's many more small particles than there are large particles. The curve is very steep. As the particles get larger, there's not many of them. And that's okay. So we've actually shot dust at our detector. We know that it can withstand that. There is some tiny probability that some huge dust particle could hit our instrument in the back of the instrument and go through the iridium layer, for example, and blow titanium out. If we see titanium, we know that happened. It's actually not a bad thing for us. So every spacecraft worries about micrometeorite environments, and so we would have the same concerns of this sort of kind of really low probability chance of something really doing damage, and that's something that every space mission worries about. The stuff around Europa is small though, and it's relatively slow compared to some of the interplanetary stuff. So 4.5 kilometers per second is fast, but it's not as fast as some stuff. All right, so this is some of the cool toys that we have to test our instrument, to calibrate it across. I mentioned this already. So in Mihai Harani's lab and Tobin and Sasha's lab, whoops, sorry about that. Okay, there's this electrostatic dust accelerator. We can accelerate dust up to 50 kilometers per second, 60, 75. So this develops a huge electrical potential, and little tiny dust particles are picked up with a charged needle, and they're accelerated down this tube all the way to a target at the end in this vacuum chamber down here, and this is where we put our instrument. So we set it at the back here, and we shoot dust into it, and so we can actually make these maps, these measurements on the ground. They're developing experiments with ice targets. And this is really interesting because what we can't do with this gizmo is shoot ice particles, which like you see at Europa. We can shoot metallic particles, we can shoot minerals that are covered in metallic particles, but we need something that is conductive, that we can accelerate down this accelerator. And so so this is where they grow ice, really pure ice, or ice that's specifically set, its composition is specifically set to be something interesting from a science point of view, and then you actually shoot metallic particles at it, and you look at what happens when it hits the ice. And so this is sort of backing into some of the physics of an ice particle hitting the target. Okay, so getting to Europa isn't easy. All right, so we have all the typical engineering challenges that you might have for a space mission: schedule and budget. I spend a lot of time worrying about this, unfortunately. The launch environment, okay, that's tough. The vacuum of space, low risk, high reliability design is challenging. Calibration and validation for a space instrument is challenging. Okay, but Europa Clipper has some extra special challenges for us. Okay, first, potential 7.5-year cruise. So whatever we do, we design this door mechanism. It's going to have to stay shut for 4 years. We have to make sure it opens after that 4-year period. That's not something. It's something that you need to worry about, and it's not easy to prove out on the ground when you don't have 4 years to do a test. Jupiter is really cold, so at a little over 5 AU, only 4% of the solar flux at Earth. And so solar power is not an abundant resource when you get to Jupiter. So you have to have, not only are you cold from a thermal point of view, the hydrazine in the prop tanks wants to freeze. We don't have a lot of power to keep it warm. We don't have a lot of power to operate our instruments. So these are all challenges. Oops, wrong way. Interplanetary cruise is hot, and so we design a spacecraft and an instrument. We want to keep it really warm. We put special coatings on it. We do all this stuff to keep it warm. But we also have to survive this interplanetary cruise where we fly by Venus at 0.65 AU. And so this is 240% of the solar flux at Earth. All right. The mission design is really hard from a fault protection point of view, and that's really, and let me explain what that means. This is a 2-week orbit, so it's 14-day orbit. that the spacecraft has around Jupiter. And some of the instruments do science over a longer period of time, but SUDA is really interested in 10 minutes of the flyby. This is where we see the dust. And so if we have an upset, if we lose communication with the spacecraft computer, we might lose an entire flyby because it's gone in a blink. Okay, so we're designing smarts into our instrument. We're designing it to be robust to faults. The spacecraft, for a lot of our low Earth orbit instruments, what we do, if anything goes wrong, the instrument just basically goes into a safe mode, raises its hand and says, ground, please help me. We can't do this here. Okay, so in this case, we have to have a smart instrument. We lose the spacecraft, we keep taking data. Something weird happens, we have to make sure that that's not a catastrophic failure. Do we just keep going? So it's a tough challenge. Coupled with that is the light time. And so we could have up to a 50-minute light time at Jupiter. And that just means that you're not doing any sort of real-time diagnosis of problems. This flyby is done by the time you get the data. We're contamination sensitive. There's several instruments on this mission that are contamination sensitive. This is also a challenge. And the one I'm going to talk about the most here is the radiation environment because it's nasty. Okay, so here's a bar graph. Let me explain this. So this is total ionizing dose, TID. So this is just the total of across the spectrum of energy of ionizing radiation. This is how much makes it through 1/10 of an inch of aluminum. Okay, so we measure. So this is in K-rads. So on the y-axis here is kilorads deposited into silicon. Okay, so a typical LEO mission or a Mars mission, 20 K-rads. Okay, and this is not easy. This means that you have to have space-rated parts. It means that you have to have shielding. It means that you can't fly, stuff that's from an iPhone. It would not survive this environment. That's a harsh environment. Okay, the Van Allen probe mission. Okay, or RBSP. This is flying right now. It's studying the Earth's radiation belts, the Van Allen belts, and it flies through those belts every single orbit. Okay, so it until Europa Clipper, for us at least, this was as bad as it got. So this is 550 K-rads behind 100 mils of aluminum. So Europa Clipper is 3 megarads. So it's humongous. And so, all right. So let me talk about this a little bit. So here, all right. Jupiter has a very strong magnetic field. So the dipole is something like 20,000 times larger in magnitude than the Earth's. Okay, so that's there. And then Io. Io is really close to Jupiter. Io is very volcanically active. The volcanoes on Io spew gases, and these gases become ionized. Okay, so magnetic. So then that's ingredient number 2. 3 is the magnetic field of Jupiter is rotating once about every 10 hours. And so what it does is it accelerates these particles. And so these ionized particles get accelerated, and it forms this thing called the plasma torus, the Io plasma torus. And that Io plasma torus is in the vicinity of, so let me orient you here. So Jupiter, the bluish lines are magnetic field lines, and then the red is electron density, or perhaps sulfur ion density. And so here's Io, here's Europa, and so this is the nasty part. You can see Europa lives right there. All right. So Parker Hinton, who is a undergrad student here at LASP, works with Fran Bagenal. He created this animation, and so this is the purple lines are the magnetic field lines. This is the plasma torus, and he told me what the color gradient was, but I forgot. But I think purple and blue is higher density, and the red is lower density. But here's Europa, and you can see it's right in the thick of it. Okay. So radiation effects, just a quick, won't spend long on this. So ionizing radiation is bad, mainly for electronics, also for detectors, has effects on materials. Some of these effects are total ionizing dose. I talked about that. Displacement damage is where particles are actually causing changes to the materials, displacing things out of the lattice of materials. Single events, this is where when an ionizing particle hits, it's actually changing the state of something inside of the electronics. And so in this case, this is a little graphic that illustrates that. This is a little MOSFET transistor, and in this case, this particle comes in and it actually changes the state of that transistor. Maybe that turns your instrument off. Maybe it locks it up and you can never turn it on ever again. So dielectric charging, this is where mainly due to electrons deposit into insulators. Those insulators charge up. They may charge up to kilovolts and then discharge into something else. So you get these discharge events that disrupt other things. Detectors are a special consideration here. They can degrade because of the environment. They can also be affected by background noise. So let me talk about that for a minute. So here's our custom detector. This is our electron multiplier. As I said, it's sensitive to both ions and electrons, and radiation affects both its life and its performance. Okay, so what do we do about that? So we put shielding around it. So we put it inside of this protective housing. We actually determine the thickness and geometry of that housing with simulation. And so there's a tool called Geont and Geont 4, and it is a tool that simulates the physics of particle interaction with matter. So these particles come in, sometimes they create secondary particles, sometimes they pass through. And so we simulate our detector inside of there and find out just exactly what's happening with how well this shielding is working for us. Okay, all right, but here's the problem with SUDA is we want to fly a reflectron design. And we want better mass resolution than the CDA instrument on Cassini. And that means we have to turn the electrons back towards the detector. That means the detector has to be open and looking up into space. Okay, so the plasma and the radiation is just coming right down into the instrument, directly into the detector. So what do we do about that? So we use some rejection grids. So in this case, we have the instrument configured, I believe, in a cation mode. And so this is a rejection grid that we set to a high negative potential. So this time it's at negative 3.2 kV. So we're rejecting electrons. All right, so then ions are coming in. We have this curved grid right here, which focuses our electrons back towards our ions back towards the detector. This will also serve to reject ions that are lower energy than 2.8 kV. So that's how we help our detector. And that doesn't mean it's not effective. We still worry quite a bit about how long our detector is going to last at Europa. We take very close care of how long it's on, when it's off. We attempt to monitor the performance of the detector over the life of the mission to make sure that it's not going belly up. Okay, so from electronics point of view, so on the left-hand side here is the brute force method. And so we put here's our electronics box. It lives inside of this other box. So it's a thick-walled box inside of a thick-walled box, which is great. This is a deep space planetary mission. So this mission is just hauling literally a ton of just metal to protect it from radiation out to Jupiter. Okay, radiation tolerant parts. Okay, so just an example here of a part that we're flying. So a commercial part, this is an FPGA, and so a commercial part might cost $600. I looked this up in a catalog just a minute ago. We're flying one that's $95,000. Okay, so we solved this problem. So this is a crazy example, but it's not. We solved this problem with money. These parts are engineered specifically for radiation, to be radiation hard for difficult environments. Okay, so the impact here is mass. The impact here is money, complexity. If you're designing something, if you're for a commercial application, you have, in terms of electronic parts, your catalog is humongous. Our catalog is like a little brochure because we just don't have that many options. So it really limits us from a design point of view, and it also limits performance. And then this is actually my last real slide. I just wanted to give everyone sort of an update of where the project is here at LASP. We had a PDR at the end of January that we passed successfully. Went pretty well. We have about 28 people at LASP that are supporting SUDA, and some are full-time, some are part-time, all working. So right now we have a lot of prototype hardware that's under test. Here's some of it over here. This is our detector. We have several of these in-house that we're testing. We have a whole prototype sensor head instrument. It's hard to see with the foil in the back here, but we're demonstrating the geometry of our ion optics and the performance of the instrument. This is a prototype processor board that's downstairs in this building right now in the electrical test lab that's been testing. We're testing. This is a key component for the instrument. It does some pretty fast analog to digital conversion for this kind of, for this challenging environment. It's a pretty slick piece of engineering for this board. And then we have the target. We talked about the iridium target here. What you see here on the target is actually, all you can see is whatever it's pointed at from a reflection point of view. But this is the iridium plated target. We've actually demonstrated that technology. We're working with GILA on campus here, the Keck Lab at GILA, and we've helped them develop a huge plasma sputtering facility to get this iridium on the surface reliably and without it coming off. This has been one of those things where we've had lots of failures before we had success, but we're getting it. So next up, we're working towards an engineering model. So an engineering model is basically an instrument. It's an instrument that we're going to build that is almost flight-like, except that it's built for engineering tests, and we use it to demonstrate the design, to mitigate risk, and just part of the design process so that we can prove out the flight design before we actually build the flight instrument. And then in early 2019, we have our critical design review, or CDR. And then here's the people that I thank, that I borrowed slides from. And that's it. I'm happy to answer questions if you have any.
So you mentioned earlier that there was 2 different ways that you're actually going to get there. One of them taking like almost 6.5 years, I think you said. One was 2.5. How are you going to decide which way you're going to submit?
Yeah, so some of that is the development of the SLS. So the SLS is in development by NASA right now, and the way the schedule looks right now is we're going to be able to launch an SLS. In fact, they're written into the law that Congress wrote funding the Europa mission, says that Europa shall launch on the SLS. We know that the SLS is a development, and a development is hard. It's a hard engineering development, and so the mission at JPL has determined that we're going to be compatible with multiple launch vehicles just to be safe. Yeah.
So if the SLS doesn't work out, then you would just do it the other way.
That's right. That's right. Yep.
For your particle detectors, what do you expect for the ratio of water particles versus arguably more interesting particles?
Okay, yeah, good question. So I didn't get into that, but that is a great question. So for certain amino acids, we're trying to be sensitive to 10 parts per million. For fatty acids, down to 1 part per million. And there's a little trick to this technique associated with that, is our instrument doesn't actually have to be that sensitive. Our detector doesn't have to be that sensitive. What happens is when those particles hit, water is hard to ionize. The other stuff is a lot easier to ionize. And so there's preferential ionization going on in the impact physics. And so we actually see the contaminants in the water a lot more than we see the water. And so there's actually an amplification of those minor constituents in these impact max spectra. So it's a very powerful technique in that regard. Let's see, Tom.
So Sasha gets a stream and sees the Spectra as you planned out with acids and fatty acids.
Yep.
Would that be significant enough to demonstrate the biological activity?
It's a good question. It depends. If you just see certain amino acids can occur, I think, naturally. And I think, and Sasha can chime in on this, there's a whole field of study about chirality, about even and odd pairings of fatty acids and all of these things that potentially happen due to biological activity, at least on Earth. And so there's a whole framework of, if you see this and maybe this, but not this, then that might indicate biological activity. And so it would be certainly fascinating to see amino acids, but I think there's another step beyond that to say that, to make some sort of further confirmation of something going on from a life point of view.
Yes, so the system you have of the various voltage levels to redirect particles, what is it that physically exists there that is given that name?
So good question. So the target is a big piece of metal, so that's easy. We hook a wire up to it. Okay. Then there's grids. So we have these very porous grids, and so these grids are actually photo etched. They're very thin, and we use a photo etching technique to carve out almost all the material, and what's left is only 10% of the material. So they're 90% transparent. They're conductive grids. They're made out of metal, either stainless or aluminum, and then we apply voltage to those grids, and so there's a wire hooked up to those. We actually control the shape of the electric field with some rings that we call shaping rings, and those just help us keep it smooth and control it. And we validate all this with simulation to make sure that, as things fly, there is some ripples in the field that disturb things, and it's one of the error sources in the instrument, but we try to keep it low enough that we can still make the measurement. Yep.
With how unreliable it is, why was a solar array chosen over like an RTG?
So yeah, so there's a bunch of reasons why. One is that I believe Mars 2020 got the last RTG that was in existence. And so what it meant is that Congress actually had to pass a law to direct the DOE to make more plutonium. And so we didn't have the RTG available. The next missions coming down the line, the New Frontiers missions, potentially they're going to use the MMRTG because I think they're going to build more. But that was a challenge for Europa. It potentially meant the whole schedule had to shift. The other impact is that solar arrays are sizable. You can add half a panel, you can add a full panel. And so as you design the mission, if you start with 4 panels and you need a little more power, you can add it. It's a little more challenging to do that with the RTGs just because the quanta are a little bit bigger and the cost is huge. And so then there's all the safety stuff, the fact that you have to keep them cool on the launch pad. And so it was a huge trade that the mission went through. When we actually proposed the instrument for the mission, they were having us keep both options open and say that it could be RTG, could be solar.
With launching on like a Falcon Heavy or a Delta Heavy, open up budget for other things like that?
I don't think so. I think at this point it's pretty much fixed that the mission is moving along. I believe there's a solar array contractor that is on board for the mission right now that's spun up and working.
Okay, you mentioned you're using essentially the Xilinx FPGA, which is a logic synthesis device.
Yep.
If you have an error in that device, have you thought about how to relay out the logic to miss the damage in a bit of the components in there?
So
rewrite the equations.
Yeah, so it turns out that the failure modes for the Xilinx, you can upset the logic, okay? But a Xilinx part, you actually reprogram it every time you turn it on. And so we get around most of that with the upset rate for this mission by power cycling the instrument. And so we actually have watchdogs that watch for these things to happen and potentially decide, okay, we're actually gonna restart the instrument. We use a rad-hard non-volatile memory, a flash, to keep the image for the or actually we use an MRAM that is rad-hard that we keep the image for the FPGA in. And so anytime something happens with the FPGA, we just reprogram it. Now, that said, we don't plan to build in the capability to reprogram the FPGA on orbit. It's possible. That's not in the plan right now, although we are potentially considering doing that for, in case there is some sort of, not just with FPGA, but let's say we lost one of our ADCs and we wanted to change, we can actually change I mean, on the fly, you can actually change the pin assignments of these FPGAs because you can reload images.
What I was getting at is that how much of the logical units that you use in the FPGA, do you have a surplus of them? So that you can just by setting one bit instead of going to this part of the chip.
Oh, that's a good question. Yeah, so I'm not an FPGA expert. My understanding is that the failure modes of this are not, there's not a, we don't plan to permanently lose you know, a flip-flop inside of the FPGA or a gate in the FPGA. I think that they're upsettable with single events, but I don't think there's permanent damage mechanisms for those. There may be. We have to fly with margin. And so we do not plan to use 100% of the gates of the FPGA. That's something we don't do. Yeah.
So the Vertex 5 you showed is like 12-year-old technology.
Yeah.
Is there any chance that in the engineering window that vastly more capable?
Nope. So what happens in these is the cement is already dried in that regard, and we're far enough down the path that we're actually, you know, we're writing code, we're designing, we have a board layout for that part already. So, yeah.
Yeah, you mentioned a magnetic field early on buried in Jupiter's full 14 Gauss dipole field. I'm surprised you can even measure. Europa has its own magnetic field.
Yeah, so actually, I think there's a little bit of uncertainty about whether Europa actually has its own, whether its core actually has its own field. But what it does have is an induced field due to the co-rotating plasma. So that plasma is moving by. So Europa's, I think it's something like 14 kilometer per second orbital speed. That plasma is moving at 190 to 100 kilometers per second. It's overtaking Europa. And so that movement of that charge is inducing, and so that induced field is what we see, and it's as the spacecraft flies by, it can measure. Galileo did it. Europa's going to have better magnetometers, and it's going to be flying by at a lower altitude.
What's the significance of that magnetic field for life?
Oh, for life? Yeah, I could only speculate on that. You know, I think that the you know, what's it do for us? It certainly is good for Earth, right? For Europa, the radiation environment is really harsh. And the icy shell actually, you know, stops a lot of it. It's twofold. One, it stops some of it after a certain depth. So potentially the top surface is sterile, and the interesting things are some depth underneath. So the lander people who could probably go on and on about how far they might have to dig through the ice to get to something that isn't completely and totally toast. Yeah.
Okay, with that, I'm going to say that's the end of our main program. So if you need to get going, you can. You're going to be around a few minutes after.
Yeah.
Scott will be around. I think a few other members of the team will be if you have any more burning questions. And I'll be here too if you want to have out tours or anything else. Thanks for coming.